And now in this lecture we find out the area of the grid shape. In the drawing we have a circle. This circle is described by the quarter circle, or actually this circle, it is inside the quarter circle. We know that the radius of this circle r equals to the square root of 2 units. Again, our mission is to find out the size of this grid shape. Okay, so first of all, we define the points that are relevant to this question. We define this point as A. We define this point as B. This is the center of the quarter circle. We define this point as O. We define this point as C. We define this point as D. This point is the touching point between this small circle and the big quarter circle, so we define the touching point as E. And finally, we define, this is the center of the small circle, we define the center of the small circle as F. In the next step, we will join points F and C together by a straight line. What is the definition of line segment FC? Point F is the center of this small circle, point C is the point of the small circle itself. This is exactly the definition of a radius. So FC is the radius of the circle, is equals to the square root of 2 units in itself, according to what is given as the question. You can implement here all 1. According to all 1, the tangent to the circle is perpendicular to the radius drawn to each point of tendency. So in the drawing we have a circle and we have tangent AB, that is tangent to this circle at point M. Point M is the point of tendency, and we have the radius OM that is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AM will be perpendicular to the radius OM. So if AM is perpendicular to OM, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule 1. We can actually implement rule 1 in our drawing. Why? Because in our drawing we have the radius FC of the small circle that is drawn to point C, that is the point of tendency of tangent OD with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OD will be perpendicular to the radius CF. If OD is perpendicular to CF, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, we have here the radius FB of the small circle that is drawn to point B, that is the point of tendency of tangent AO with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius BC. If AO is perpendicular to BC, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees. So inside this small quadrilateral BFCO, we have, this is a quarter circle, and therefore this angle equals to 90 degrees. In any quarter circle, this angle equals to 90 degrees, it is a right angle. So, inside the small quadrilateral BOCF, we have 1, 2 right angles. The sum of right angles is 270 degrees, plus the size of this fourth angle. In total, the sum of those four angles must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle here must be equal to 90 degrees in its size. Again, in order to complete the sum of the angles inside the small quadrilateral BFOC to 360 degrees, the missing angle must be equal to 90 degrees in its size. So inside quadrilateral BFOC we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to this small quadrilateral BFOC as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side BF equals to the opposite side OC in rectangle BFOC. But BF equals to the square root of 2, therefore OC must be also equal to the square root of 2 units in its length. Likewise, according to the same rule, in rectangle BFOC, side FC must be equal to the opposite side BO. But FC equals to the square root of 2 units, therefore BO must be also equal to the square root of 2 units in its length. So we actually found out that quadrilateral BFOC is not a rectangle but a square. Why? Because all of its sides are equal to each other. Each side of this square BFOC is equal to the square root of 2 units in its length. In the next step, we join points O and F together by a straight line. And we focus on the right triangle FCO. In the right triangle FCO, those two sides are equal to each other. And we have the rule that in front of equal sides in the triangle, there are equal angles. So we'll focus on the right triangle BFO. In the right triangle BFO, those two sides that are equal to each other, and we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. And we also know that the sum of the angles in any triangle is equal to 180 degrees. And especially it is true in the right triangle BFO. So which angles we have in the right triangle BFO? This angle equals to 90 degrees. This angle equals to alpha, and this angle also equals to alpha. So it is 90 degrees plus alpha plus alpha. In total, they must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So in the right triangle BFO, 90 degrees plus alpha equals to 180 degrees. So 90 degrees plus 2 alpha equals to 180 degrees. Here we subtract 90 degrees from this equation, and finally we get that 2 alpha equals to 180 degrees minus 90 degrees is the 90 degrees. It is 90 degrees. So 2 alpha equals to 90 degrees. Here we divide this equation by 2, and finally we get that angle alpha equals to 90 degrees over 2, that is 45 degrees. So this is angle alpha that is equal to 45 degrees in its size. And and this is also angle alpha that is equals to 45 degrees in its size. We continue to focus on the same right triangle BFO, and we'll implement the Pythagoras law in the right and associated triangle BFO. So, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle BFO, the hypotenuse is FO, therefore the square of the hypotenuse is FO squared, and it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to BF squared plus BO squared. Repeat again, according to the Pythagoras theorem, in the right and associated triangle BFO, FO squared equals to BF squared plus BO squared. So FO squared, that is the square of the hypotenuse, equals to BF squared. BF is square root of 2, therefore BF squared is square root of 2 squared, that is 2, plus BO squared. BO is also square root of 2, therefore BO squared is square root of 2 squared, that is 2. So in conclusion, we found out that FO squared equals to 2 plus 2, that is 4. FO squared equals to 4. Here we'll take a root out of this equation, and we get that FO equals to the square root of 4, that is 2. So FO equals to 2 units in its length. My segment FO, or the hypotenuse FO, equals to 2 units in its length. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is Rule 9, and according to Rule 9, if two circles touch each other internally, here we have in the drawing the big circle touches the small circle, this small circle at point P. Point P is their touching point or their point of tendency. So those two circles touch each other internally at point P. So if two circles touch each other internally, then the straight line that connects their centers together must pass for their touching point. The center of this circle is 0 at point O, the center of this circle is 0 at point M, and the straight line that connects their centers together is the straight line OM, and according to this Rule 9, the straight line OM must pass for their touching point. That is to say, OM must pass for point P, that is their touching point. Or OMP is one straight line. Again, OMP is one straight line. So actually, we can implement Rule 9 in our drawing. Why? Because in our drawing, the center of this quarter circle is here at point O. The center of this small circle is here at point F, and the straight line that connects their centers together is OF. And but before that, here the small circle touch the big circle, the big quarter circle at point E. They touch each other internally because The small circle is located inside the quarter circle. Therefore, this is the case when the two circles touch each other internally. Whenever we have two circles that touch each other internally, you can implement rule 9. Therefore, we can implement rule 9. And according to rule 9, the straight line that connects the centers together, that is OF, must pass through their touching point. Your touching point is here at point E. That is to say, OF, the straight line OF must pass through point E, or OFE is one straight line. Again, OFE is one straight line. So here, the straight line OF must pass from point E. Here, the straight line OF, it passes through point E, that is the touching point of the small circle with this quarter circle. Or OFE is one straight line. OFE is one straight line. And point O is the center of the quarter circle. Point E is the point of the quarter circle itself. Therefore, OE is the radius of this quarter circle. We define the radius of this quarter circle as capital R. And we know that capital R equals to OE. And according to rule 9, OE is a straight line, or OFE is one straight line. What is the length of OFE? OFE equals to OF plus FE. The reason that OFE equals to OF plus FE is because OFE is one straight line. Therefore, OFE equals to OF plus FE. That is to say, OE equals to OF, that is 2. What is the length of FE? Point F is the center of the small circle, point E is the point of the small circle itself. Therefore, FE is the radius of the quarter circle, that is equals to the square root of 2 units in its length. So FE equals to the square root of 2 units. So in conclusion, found out that capital R, that is the radius of the quarter circle, equals to 2 plus square root of 2 units in its length. And we know that OE or OFE is one straight line. We define the intersection point of line segment OF with this small circle as H. If OFE is one straight line, it means that edge FE is also one straight line, because edge FE is part of OFE. So edge FE is one straight line, and edge FE is a line segment, is a straight line that touches the small circle at point H and at point E. Therefore, edge E is a chord inside the small circle, but edge FE is a chord that passes through the center of this small circle, that is to say from point F. Therefore, edge FE is the diameter of this small circle. So edge FE is the diameter of the small circle. Edge FE is the diameter of the small circle. We know that the diameter of any circle bisects the circle into two halves. This is the first half and this is the second half. In conclusion, you can say that this is a semicircle. So you can write here that this is a semicircle. This is a semicircle of the small circle. Okay. What is the definition of a sector? Here, this green shape is a sector. A sector is part of a circle. If the circle is a cake, then a sector is a slice of cake. A sector is a slice of cake. So the sector AOB consists of two legs. The first leg is AO and the second leg is BO. The two legs of this sector, AO and BO, they are both the radii of this circle is equal to R. And the angle between the legs of this sector, of the green sector AOB, is theta. So what is the area of this green sector AOB? The area of the sector equals to pi r squared, that is the area of this circle, times theta, that is the angle between the legs of this sector AOB, over 360 degrees. Repeat again, the area of this circle equals to pi r squared, that is the area of the circle, times theta over 360 degrees. Again, theta is the angle between the legs of this sector. So the area of any circle, or the area of any sector, equals to pi r squared, that is the area of the circle, times theta over 360 degrees. Okay. So our mission is to find out the area of this green shape. What is the area of the green shape? From the drawing, it is very easy to see that the area of this green shape, equals to the area of sector AOE that is how we write the area of sector AOE. This sign above AOE is a sign for a sector, so it is the area of sector AOE minus the area of this small semicircle minus the area of this small shape HBO. Minus the area of the orange small shape HBO. Repeat again, the area of this green shape equals to the area of sector AOE minus the area of the semicircle minus the area of this orange shape BHO. The area of the green shape in total, it is equals to the area of sector AOE minus the area of the semicircle minus the area of the small orange shape BHO. Okay, the area of sector AOE minus the area of this semicircle minus the area of this orange shape will be equal exactly to the area of this green shape. It is very easy to see it from the drawing itself, from this drawing. Okay, so first of all, we have to find out the area of this sector AOE. What is the area of sector AOE? know that the area of any sector equals to the area of the circle that contains the sector. In this case, the big circle contains this sector AOE. So the area of the big circle will be equal to pi times capital R squared. And we have to multiply it by angle theta. Angle theta is the angle between the legs of this sector AOE. This angle theta equals to 45 degrees in its size over 360 degrees. So the area of the big sector AOE equals to pi times R squared. We have already found out that times capital R squared, and we have already found out that capital R equals to 2 plus square root of 2 units. If capital R equals to 2 plus square root of 2, it means that capital R squared equals to 2 plus square root of 2 squared. And 45 degrees over 360 degrees, it is 1/8 or 1 over 8. So we have to divide it by 8. So the area of the big sector AOE will be equal to pi times 2 plus square root of 2 squared. 2 plus square root of 2 squared equals to 2 squared, that is 4, plus square root of 2 squared, that is 2, plus 2 times 2 times square root of 2 divided by 8. So it is pi, inside the brackets we have 4 plus 2 is 6, and we have here 2 times 2 is 4, so in total this expression equals to 4 times square root of 2 divided by 8. So here we will divide both the numerator and the denominator of this expression by 2, and we get that finally the area of the big sector AOE will be equal to pi, inside the brackets we have 6. 6 over 2 is 3, plus 4 times square root of 2 over 2 is 2 times square root of 2 over 8. We have to divide the denominator 8 by 2, so 8 over 2 is 4. So in conclusion, we found out that the area of the big sector AOE the area of this big sector AOE is equals to pi times 3 plus 2 times square root of 2 over 4 square units. In the next step we will find out the area of this semicircle. The semicircle is part of this small circle that its radius is r. So the area of the small semicircle will be equal to pi r squared over 2. The area of the semicircle equals to pi, and r is square root of 2, according to what is given as a question. If r is square root of 2, it means that r squared is square root of 2 squared, that is 2, divided by 2. 2 2 over 2 is 1, so we left only with pi. In conclusion, we found out that the area of the small semicircle is equals to pi square units In the next step we find out the area of this orange shape B edge O. What is the area of the orange shape B edge O? From the drawing it is very easy to see that the area of this orange shape BHO will be equal to the area of triangle BFO minus the area of this small sector FBH. Repeat again. The area of the orange shape BHO equals to the area of the right triangle BFO minus the area of the small sector FBH. Okay, so the area of the orange shape BHO is equals to the area of this right triangle BFO. So what is the area of the right triangle BFO? The area of any triangle equals to the base of the triangle times the height to the base over 2. The base of the triangle is square root of 2 and the height of the triangle is also square root of 2. So the base times the height is square root of 2 times square root of 2 divided by 2. Square root of 2 times square root of 2 is 2 and 2 over 2 is 1. So in conclusion, we found out that the area of the right triangle BFO is equals to 1 square units minus the area of the small sector FBH. What is the area of the small sector FBH? The area of any sector equals to the area of the circle that contains the sector, that is actually pi r squared, times the angle between the legs of the sector, that is 45 degrees, over 360 degrees. So it is pi and r is square root of 2, therefore r squared is square root of 2 squared, that is actually 2. And 45 degrees over 360 degrees is 1 over 8. So we divide it by 8. So the area of the small sector BFH equals to pi and square root of 2 squared is 2 over 8. Here we divide both the numerator and the denominator by 2. 2 pi over 2 is pi and 8 over 2 is 4. So in conclusion, we found out that the area of the small sector BFH is pi over 4 square units, and we already found out that the area of the right triangle BFO is 1 square unit. So in total, the area of the orange shape BHO is equals to 1 minus pi over 4 square units. repeat again that the area of the green shape is equals to the area of the big sector AOE minus the area of this small semicircle minus the area of this orange shape BHO. Repeat again, the area of the green shape, in total it is equals to the area of sector, the big sector AOE minus the area of the small semicircle minus the area of the orange shape BHO. So the area of the green shape in total will be equal to the area of the big sector AOE, and we already found out that the area of the big sector AOE equals to pi times 3 plus 2 times square root of 2 over 4 square units minus the area of the semicircle. We already found out that the area of the semicircle is pi, so it is minus pi minus the area of the orange shape, and we already found out that the area of the orange shape BHO is equals to 1 minus pi over 4 square units. So this expression in total it is equals to the area of the green shape. So we'll open the brackets here and we get that the area of the green shape equals to pi. Inside the brackets we have 3 plus 2 times square root of 2 over 4. We have here minus pi, and we'll open the brackets here. Here we get here that it will be equal to minus 1, and minus times minus is plus, so it is minus 1 plus pi over 4. So the area of the green shape equals to, here we have pi times 3 plus 2 times square root of 2 over 4, and we have here minus pi plus pi over 4 is minus 3 quarters pi minus 1. So you will multiply minus 1 by 4, and then we'll divide it by 4 in order to have a common factor with the other two expressions. Minus 1 times 4 is minus 4 divided by 4. So here we have on all the three expressions we have in the denominator so 4. So 4 will be the common factor of those three expressions. We'll open the brackets here, and we get that pi times 3 is 3 pi, plus 2 times square root of 2 times pi is 2 times square root of 2 times pi, and we have here minus 3 pi minus 4. So here we have 3 pi minus 3 pi is 0, so 3 pi will get cancelled, and we're left only with 2 times square root of 2 pi over 4 minus 4. So here we divide both the numerator and the denominator of this expression by 2, and we get that 2 times square root of 2 times pi over 2 is square root of 2 times pi. Minus 4 over 2 is minus 2. And we have to divide the denominator of 4 by 2. So 4 over 2 is 2. So in conclusion, we found out that the area of the green shape equals to the square root of 2 times pi minus 2 over 2 square units, or in terms of numbers, it is equals to 1.2214 square units. Repeat again. The area of this green shape equals to either square root of 2 pi minus 2 over 2 square units, or in terms of numbers, the area of this green shape equals to 1.2214 square units. Okay, so in the next step I will summarize the lecture. In this lecture, we found out the area of this green shape. In the drawing, we have a circle inside this quarter circle. We know that the radius of this small circle r equals to the square root of 2 units, and our mission is to find out the area of this green shape. Okay, so the first step, we defined the relevant points to this question. Here we defined this point as A, we defined this point as B. This is the center of the quarter circle. We define this point as O, we define this point as C, we define this point as D, and this is the touching point between the small circle and the quarter circle. We define the touching point as E. And finally, we define the center of this small circle, this point as F. Then we joined points F and C together by a straight line. Point F is the center of this small circle, point C is the point on the circle itself, therefore line segment FC is the radius of this circle. This is equal to the square root of 2 units according to what is given in the question. And we have the radius FC that is drawn to point C, that is the point of tendency of tangent OD with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OD will be perpendicular to the radius CF. If OD is perpendicular to CF, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, line segment FB is the radius of this circle that is equal to the square root of 2 units. We have the radius FB that is drawn to point B, that is the point of tendency of tangent AO with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius BF. If AO is perpendicular to BF, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. So inside quadrilateral BFOC, this small quadrilateral BFOC, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. 270 degrees plus the size of this fourth angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any triangle, the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore the missing angle here must be equal to 90 degrees in its size. Again, in order to complete the sum of the angles inside quadrilateral FBOC to 360 degrees, the missing angle must be equal to 90 degrees in its size. So quadrilateral BFOC has 4 right angles, therefore quadrilateral any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to this small quadrilateral BFOC as the rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side BF must be equal to the opposite side OC in rectangle BF OC. But BF equals to the square root of 2, therefore OC must be also equal to the square root of 2 in its length. Likewise, according to the same rule, side FC must be equal to the opposite side BO. But FC equals to the square root of 2, therefore BO must be also equal to the square root of 2 in its length. So actually found out that quadrilateral BFOC is not a rectangle but a square because all of its sides are equal to each other. In the next step, we join points F and O together by a straight line and focus on the right triangle FBO. In the right triangle FBO, those two sides, each side equals to the square root of 2 in its length, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. And we also know that the sum of the angles in any triangle is equal to 180 degrees, and especially it is true in the right triangle FBO. So which angles we have inside the right triangle FBO? We have this angle that is alpha, the other angle that is alpha, and this angle equals to 90 degrees. So in the right triangle FBO, 90 degrees plus alpha equals to 180 degrees. So 90 degrees plus 2 alpha equals to 180 degrees. We subtract the 90 degrees from this equation and finally found that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. So 2 alpha equals to 90 degrees. We divided this equation by 2 and finally found out that the missing angle alpha equals to 45 degrees in its size. This is angle alpha that is equals to 45 degrees in its size. This is also angle alpha that is equals to 45 degrees in its size. Then I presented to you rule 9 and we implemented rule 9 in our drawing. According to rule 9, if two circles touch each other internally, here we have in the drawing two circles. Those two circles touch each other internally at point P. Because of the fact that the small circle is located inside the big circle, the two circles touch each other internally, and so they touch each other internally at point P. And according to this rule 9, whenever you have an internal notch between two circles, that is to say they are touching each other internally, like in this drawing, then the straight line that connects their centers together, here, the center of this big circle is here at point O, the center of this small circle is here at point M, and the straight line that connects their centers together is the straight line OM. According to this rule 9, the straight line OM must pass through their touching point, that is point P. So the straight line OM must pass through point P, or OMP is one straight line. Again, OMP is one straight line. We can actually implement rule 9 in our drawing. Why? Because in our drawing, this small circle touches this quarter circle at point E. And because of the fact that the small circle is located inside the big quarter circle, it means that the two circles touch each other internally at point E, here. Whenever we have an internal notch between two circles, you can implement rule 9. Therefore, you can implement rule 9 in our drawing. Those two circles touch each other internally at point E. The center of the quarter circle is here at point O. The center of this small circle is here at point F. The straight line that connects their centers together is the straight line OF. And according to this rule 9, the straight line OF must pass through their touching point. That is to say, the straight line OF must pass through point E, that is their touching point. Or OFE is one straight line. OFE is one straight line. If OFE is one straight line, it means that OFE is also the radius of the quarter circle. Why? Because point O is the center of the quarter circle, point E is a point on the quarter circle itself. This is exactly the definition of a radius. So OFE is the radius of the quarter circle. We define the radius of the quarter circle is R. Therefore, OFE equals to, we define the radius of the quarter circle is capital R. Therefore, OFE equals to capital R, that is the radius of the quarter circle. So OFE is one straight line, and it is also the radius of the quarter circle that is equal to capital R. So OFE, what is the length of line segment OFE? This is also the radius of the quarter circle. OFE equals to OF plus FE. Again, OFE equals to OF plus FE. OF equals to OF plus FE. OF equals to 2 and FE equals to the square root of 2. So in total, OFE equals to 2 plus square root of 2. That is to say, the radius of this quarter circle that is equal to capital R, according to our definition, equals to 2 plus square root of 2. So according to rule 9, OFE is one straight line. If OFE is one straight line, it means that edge FE is also one straight line, because edge FE is part of OFE. Therefore, edge FE is also one straight line, but edge FE is one straight line that touches the small circle at point E and also at point H. And any straight line that touches the circle at 2 points must be the chord of the circle. So edge FE is the chord of the small circle, and edge FE is a chord that passes through point F, that is the center of the small circle, and any chord that passes through the center of the circle must be the diameter of the circle. Therefore, edge FE that passes through point F, that is the center of the small circle, must be the diameter of this small circle. So edge FE is the diameter of the small circle, and we know that any diameter of any circle bisects the circle into 2 halves. So edge FE, the diameter of this circle, bisects this circle into 2 halves. This is the first half and this is the second half. Therefore, this is a semicircle and this is also a semicircle. In conclusion, we found out that this shape edge BE is a semicircle. So this is a semicircle. Okay. And in the next step, I presented to you the definition of a sector. The green shape here is a sector. A sector is part of a circle. A sector is like a slice of a cake. If a cake is the circle itself, then a slice of a cake is a sector. So A or B is a sector. The sector A or B consists of 2 legs. The first leg is AO and the second leg is BO. Those 2 legs are both the radii of this circle that is equal to R, and the angle between the legs of this sector, is theta. So what is the area of this green sector A or B? The area of this green sector A or B will be equal to pi r squared, that is the area of the circle, times theta over 360 degrees. Again, theta is the angle between the legs of this green sector A or B. So, in conclusion, we found out that the area of any sector equals to pi r squared, that is the area of the circle that contains the sector, times theta over 360 degrees, and again theta is the angle between the legs of the sector. Okay. Our mission is to find out the area of this green shape. What is the area of the green shape? From the drawing, it is very easy to see that the area of this green shape will be equal to the area of sector AOE, this big sector AOE, minus the area of this semicircle, minus the area of this orange shape BHO. Again, the area of this green shape will be equal to the area of sector AOE, this sector AOE, minus the area of this small semicircle, minus the area of this orange shape BHO. Repeat again. The area of the green shape must be equal to the area of the big sector AOE minus the area of the small semicircle minus the area of the orange shape BHO. So first of all, we found out the area of the big sector AOE. The area of any sector equals to the area of the circle that contains the sector. AOE is part of the big circle, and the radius of the big circle is capital R. Therefore, the area of the big circle must be equal to pi times capital R squared. So the area of the circle that contains the sector is pi times capital R squared times the angle between the legs of this sector is 45 degrees. So it is times 45 degrees over 360 degrees. We have already found out that capital R equals to square root of 2 plus 2. Therefore, capital R squared equals to square root of 2 squared. Therefore, in total, the area of the big circle will be equal to pi times 2 plus square root of 2 squared. And 45 over 360 degrees is 1 over 8. So we have to divide the area by 8. So what is the value of this expression? It is equals to pi, and 2 plus square root of 2 squared equals to 2 squared, that is 4, plus square root of 2 squared, that is 2, plus 2 times square root of 2 divided by 8. So here we have pi, inside the brackets we have 4 plus 2 is 6, and 2 times 2 is 4. So in total, in the numerator of this expression, we have 4 times square root of 2 divided by 8. Here we divided both the numerator and the denominator of this expression by 2. So in the numerator we have pi, and inside the brackets we have 6. 6 over 2 is 3, plus 4 times square root of 2. 4 over 2 is 2, so in total this expression after we divided by 2 will be equal to 2 times square root of 2 divided by 8. So here, in total, in the numerator, after we divided by 2, we will have pi times 3 plus 2 times square root of 2, and we have to divide the denominator 8 by 2. 8 over 2 is 4. So here we have 4 in the denominator. So in total, we found out that the area of the big sector AOE equals to pi. Inside the brackets we have 3 plus 2 times square root of 2 over 4. So we have to find also the area of the small semicircle. What is the area of this small semicircle? This semicircle is part of this small circle. And we know that the radius of this small circle is R. So the area of the semicircle equals to pi R squared, that is the area of the small circle, over 2. According to what is given as the equation, R equals to the square root of 2, therefore R squared equals to the square root of 2 squared, that is 2. So in total, the area of the small circle equals to 2 pi over 2. That is the area of the semicircle, when we divide it by 2. 2 over 2 is 1, so left only with pi. So in conclusion, we found out that the area of this small semicircle equals to pi square units. The area of the small semicircle equals to pi square units. And we have to find out also the area of this orange shape, BHO. What is the area of the orange shape, BHO? From the drawing, it is very easy to see that the area of the orange shape, BHO, equals to the area of the right triangle FBO minus the area of this small sector FBH. Here again, the area of the orange shape BHO in total is equals to the area of triangle BFO, the right triangle BFO, minus the area of the small sector FBH. The area of any triangle is the base of the triangle times the height over 2. Here, because of the fact that triangle FBH is a right and an isosceles triangle, those two sides are equal to each other. So the base equals to the square root of 2 units, and the height also equals to the square root of 2 units divided by 2. So in total, the area of the right and associated triangle FBO equals to square root of 2 times square root of 2 is 2 divided by 2. 2 over 2 is 1. So the area of the right and associated triangle FBO is 1 square units. And we have to subtract from the area of this triangle FBO the area of this small sector FBH. The area of sector FBH will be equal to the area of this circle that contains the sector. The area of the circle that contains the sector is pi r squared, and the angle between this small sector is 45 degrees. So it is 45 degrees over 360 degrees. R equals to the square root of 2, therefore r squared is square root of 2 squared. So in total, the area of the small circle is pi times square root of 2 squared, and 45 degrees over 360 degrees, it is 1 over 8, so we have to divide this expression by 8. So here, in total, the area of the small sector BFH will be equal to pi times square root of 2 squared is 2 over 8. Here we divided this expression, both the numerator and the denominator of this expression, by 2. So 2 pi over 2 is pi, and 8 over 2 is 4. So in total, we found out that the area of the small sector BFH is equals to pi over 4 square units. Therefore, the area of the orange shape in total will be equal to the area of triangle BFO, that is 1, minus the area of the small sector FBH, that is pi over 4. So in total, the area of the orange shape BHO equals to 1 minus pi over 4 square units. And the area of the grain shape, the area of this grain shape equals to the area of sector, the big sector AOE, minus the area of this semicircle, minus the area of this orange shape PHO. It again, the area of the grain shape in total it equals to the area of the big sector AOE, minus the area of the small semicircle, minus the area of the orange shape PHO. We have already found out that the area of the big sector AOE equals to pi times 3 plus 2 times square root of 2 over 4, minus the area of the small semicircle, that is pi, minus the area of the orange shape BHO, that is 1 minus pi over 4. So it is equals to pi times 3 plus 2 times square root of 2 over 4. Here we have minus pi. We open the brackets here, so it will be minus 1. After we open the brackets, it will be here minus 1, and minus times minus is plus, so it is plus pi over 4. So the area of the grain shape in total will be equal to pi. Inside the brackets we have 3 plus 2 times of 2 over 4. Here we have minus pi plus pi over 4 is minus 3/4 pi. Here we multiplied 1 by 4. We multiplied minus 1 by 4, and then we divided by 4 in order to have a common factor with the other two expressions. So 1 times minus 4 is minus 4, so, and we have to divide it by 4. Here we open the brackets, pi times 3 is 3 pi, and 2 times square root of 2 times pi is 2 times square root of 2 times pi, and we have here minus 3 pi minus 4. 3 pi minus 3 pi is 0. After we cancel 3 pi, we left only with 2 times square root of 2 times pi minus 4 divided by 4. Here we divided both the numerator and the denominator of this expression by 2. So 2 times square root of 2 times pi is square root of 2 times pi, and minus 4 times 2 is minus 2, and we have to divide the denominator of 4 by 2. 4 over 2 is 2. So in conclusion, we found out that the area of this green shape equals to either square root of 2 times pi minus 2 over 2. In terms of numbers, the area of this green shape equals to 1.2214 square units. Okay, thank you very much.